So when we looked at moments, I introduced the principle of moments, which says that if an object is in equilibrium, that the sum of the clockwise moments must equal the sum of the anti-clockwise moments. Now, that is not the only condition required for equilibrium. So we're going to have a little look at equilibrium as a bigger topic now. So when a body is in equilibrium, there are two options. It can either be at rest, or it can move with a constant linear velocity and rotational velocity as well, which is an idea we should be happy with. So we've talked about this idea where if forces are balanced, then nothing really happens, nothing changes, and that's what we mean by equilibrium. So the conditions for equilibrium, well, we've actually already met both of them. I've just reminded you of one, and in fact I've just reminded you of the other. So resultant force on the body must be 0, and the principle of moments must apply about any point on the body. So those are our conditions for equilibrium. Now, we've often only thought about simple situations where we've only got 2 forces, or we've got 3 forces but they're all coplanar. What we're going to think about is what happens if we have 3 forces that are not coplanar. And in that case, it's actually not that difficult. The 3 forces acting on the body, if it's in equilibrium, would form a closed triangle. So if we think about this object here, so I've got an object sitting on a slope, so there is the normal supporting force from the ground, there's the friction that's acting this way, and there's the weight that's acting straight down. Now what I could do is, say, split the weight into its 2 components, so that it's got a component that's parallel to support and a component that's parallel to the friction, and I could figure out that way if it was balanced. Or I could just draw them to scale. So if I draw my W going straight down, my weight going straight down, my friction at the angle that it's going and the length that it's going, then my support force in there, it gives me what we'd call a closed triangle of forces. So I've ended up where I started because I went one to the other. And if I ended up where I've started, then I have no resultant force. The forces are actually all balanced. Okay. So another example, if I've got a spider hanging on a piece of thread and it's been blown by the wind, we want to know if it can hang in equilibrium. Well, we've got the tension of the thread pulling that way, we've got the wind pushing it completely horizontally, fancy that, and a weight that's going straight down. Well, again, I can just combine these into a triangle of forces. And by doing that, I can actually also figure out at exactly what angle the string will be, so I could tell something about where the spider would be because of the wind, which would be interesting. So if I know they're in equilibrium, I know that they will go together to make a nice triangle. So again, oh look, here comes back all that stuff about vectors and trig. You can just feel it lurking in the background, can't you? All these ideas getting used again and again and again. Get used to it. But this is pretty easy, this stuff, really. You'll be absolutely fine with it, I know. So this idea of equilibrium, there's a couple different ways we can use it. If we work out that the resultant force on an object is 0, then we know the object's in equilibrium. Yay! If we know it's in equilibrium, then we could use it to figure out one of the forces. So we could figure out an unknown force, or we could figure out, as I just pointed out, an unknown angle. So knowing this principle allows us to figure more stuff out. The conditions I said at the beginning, learn them, learn what they're for. They are a nice, easy 2-mark question if they come up on an exam, so make sure you know them. Okay, that's it. Short and sweet. Remember, any questions? Ask me when you see me.